Any guesses? You know what that list is at the top? No. No. That's the list of our strong acids. So HCl, H2SO4, HBr, HNO3, HClO3, HClO4, and HI. Those are the acids that are considered strong. Will you tell your partner what strong means one more time? It completely dissociates in water. Thank you for telling me, Diane, and everyone else that got to enjoy that definition, because she's right. It means it completely dissociates in water. So that's what this example is. Sometimes, by the way, this is called a hydrolysis reaction. Hydrolysis reaction just means you're adding something to water and it breaks apart. So what happens is you create the hydronium ion, which is H3O+, and then this anion called the chloride ion. This is an acid right here, which means the water must be acting like a what? Base. This is an anion that came from the acid, so what would we call this? Conjugate base. And then the hydronium would have been the conjugate, or would be the conjugate acid. Okay? Now, we kind of went over this on Friday, but it's one of the reasons, another way I should say, to define this as a strong acid. H2O is a much stronger base than Cl-, so the equilibrium lies so far to the right, K is not even measured. All right? We're going to learn, and most likely today, about this idea of Ka. Ka is the equilibrium expression for an acid. It's pretty much always the same. Ka will be equal to H plus times your anion, which is written as A minus, over your acid, which is HA. All right? That's the general statement for Ka. And what we're saying here, for a strong acid, since it pretty much 100% ionizes, these are a very large number, and that's 0. Since we can't divide by 0, that's undefined, well, then we say the same thing, then, that we don't have a Ka for a strong acid. We don't even worry about defining it, because it's not in equilibrium with products and reactants. It's all products and 0 reactants. Okay with that so far? Okay? Now, that only applies to these strong acids. Everything else, by definition, would be a weak acid. And in a weak acid, only part of it dissociates. So we will actually have a Ka value. Now, I'm kind of going out of order here, but the super nice thing about Ka, if you think about it, these two numbers are always equal. Because, well, as long as it's a monoprotic, which it will be. Because when HA broke apart, it broke into 1H and 1A. So Ka for just a weak acid, we typically say it's just equal to x squared over my initial minus x. Now, here's what's even cooler. X is extremely small. So if x is really small, I'm going to ignore it right here. And by the way, that x squared minus initial minus x came from an ice table. But if this is so small that mathematically it's insignificant, then don't even do it. So we end up with that Ka equals x squared over initial, and it's going to be very useful. Now, that's actually coming up in a while, but there's your intro to it. All right. This time, acetate is a stronger base than water, so the equilibrium favors the left side. All right, so our products are small, our reactants are still large, so now we would have a Ka for weak acids. The two main weak acids we'll talk about in this class are usually acetic acid, which is HC2H3O2, and that's vinegar. All right, or acetic acid. We talk about that one and use it a lot. And then the only other one we really usually talk about is HF, hydrofluoric acid, which is a very weak acid because F is really strongly holding on to H. Okay? In these, they don't dissociate as much, so they have Ka values. All right, the majority of the rest of the hour we're going to talk about pH. So to do that, first we got to talk about water and its autoionization. As we have seen, water is amphoteric. Will you tell your partner what that means? It means it can act like an acid or it can act like a base. All right. In pure water, a few molecules act as a base and a few act as an acid. This is referred to as autoionization. It's when two water molecules collide. Those collide and transfer a hydrogen ion, and you get some H3O plus and you get some OH minus. This is acidic, this is basic. Now, the good thing about this, since it's just in pure water, they end up being equal to each other. Okay? Now, this reaction is typically not written this way, it's written this way, where one water molecule just breaks apart into H plus plus OH minus. Okay? This is called hydronium. This is called hydronium. This is hydroxide, and this is exactly the same, so it's also hydroxide. You can see this written in either case. Now, this is probably a little out of order, but whatever. So, we're going to talk about pH here in a second, but in this class we will also talk about pOH, pKa, pKb, and pKw. Now, that's a lot of stuff, but you'll notice it's all the same math. In science, if we take P, we are taking or finding the power of whatever's left. So here we would say power of the hydronium ion, power of the hydroxide ion, power of the Ka, power Kb, power of Kw. And what we mean by power is an exponent. We're finding the exponent that the thing is raised to. Now in mathematics, there's a tool that finds me exponents, and that tool is called the log. Okay? And we're going to use the log base 10. That looks like a 16. Log base 10. When we're using log to the base 10, we're saying, okay, what exponent is 10 raised to that gave me this value? That's all logs are doing. Like, we overthink them, but they're really just exponent finders, or they're power finders. So whenever you see P and then something else, you're just taking the negative log of it. It's negative so that our values end up being positive numbers, because these exponents we're finding are negative exponents, meaning these are numbers less than 1. Not negative numbers, but just exponents that are negative. All right, kind of okay with that? So we'll spend today just on pH and pOH. So pH means the negative log of the H plus. pOH means the negative log of the OH minus. Okay. So this really goes with the slide before it. I should fix that. So the equilibrium expression for this process would be Kc equals H3O over OH minus. Do you know why the H2O is gone? The reason it's gone? That's true, but that's not the real reason why. The real reason why is because we don't put solids or liquids in our equilibrium expressions. We just put ions or pressures of gases. All right, this special equilibrium constant is referred to as the ion product constant for water, and at 25 kW always is 1 times 10 to the negative 14. So H3O concentration times OH minus concentration always equals 1 times 10 to the negative 14. Another way to write it, H plus concentration times OH minus concentration always equals 1 times 10 to the negative 14. Now we're going to have to use this. This is given to you on the AP test, so it's not one you have to memorize, even though it's kind of easy. You're going to use this because sometimes you'll be given this and you'll be asked for that. And that's pretty easy. You always take 1 times 10 to the negative 14 and you divide it by the given. And that will always tell you what you want. Now, this 14 isn't a random number. You may recall that the pH scale goes between 1 and 14. It absolutely has to do with this exponent right here. Sweet. Just put it right there by that other box. Thank you. All right. Now, the math for pH, you have to know this equation. pH is defined as the negative base 10 logarithm of the hydronium ion concentration. All right? So you just literally type that into your calculator. Make sure and use the negative button and not the minus button. They are different. Anyone need a calculator? Yeah, that says -3. So you would just hit negative log 0.0028. You hit enter, and what do you get? 2.95? 55, sorry. Okay, and that's your pH. Really, really easy. All right, try another one. H plus equals 1.96 times 10 to the negative 8. What is your pH? All right, what did we get? Someone louder? 7 point what? 7. Okay. Whoops, I don't need the times 10. That was the other part. 7.7. Not bad, right? Okay, now you do need to know how to go both directions. So if I tell you the pH equals 11.2, and I want to know the H plus concentration, we have to know how to go both ways. Okay, so It's not bad. We need to take the inverse log of the negative pH. The inverse log, what, Diane? Okay. The inverse log on your calculator, you just hit second log, and you get 10 to the x. That's what inverse log is. All right, and then we need the negative pH. And that's how you can solve for the H plus concentration. So we would just put in 10 raised to negative 11.2. You're going to get some small number. What's that? Okay, that's a really small number, but that's okay. Because this solution's pretty basic, right? And if it's basic, that means the H plus concentration is really low. And this shows that it is. All right, now, let's take it another step. We know this. What's the OH minus concentration? All right, I don't know either, but I know how to figure it out. So we just had an equation where we said H plus times OH was 1 times 10 to the negative 14, right? So I know my H plus, so I'm going to do this. I'm going to take 1 times 10 to the negative 14. 14, Tom. There we go. And that's a constant. Okay? And I'm going to divide it by my H plus value, which I just found right here, right? 6.3 times 10 to the negative 12. And I'm going to just type that in, and that's a lot of typing, but it's okay. So 0.0015, if you wrote that in exponential notation, it'd be 1.5 times 10 to the negative, and then you would just count over 1, 2, 3. Either way is fine, by the way. So far, okay? It's a combination of two, I guess 3, technically, equations. That my pH is equal to my negative log. My H plus is equal to 10 raised to the negative pH. And that my H plus or my OH would be equal to 1 times 10 to the negative 14 divided by my given. Okay, there's one more piece to this puzzle. It's not hard. And that is the POH. So POH is simple. It equals the negative log of the OH minus concentration. Why are you so lame lately? Okay. What did we find? We were finding the concentration of hydroxide. Right here? Yeah, that's the concentration of the OH minus. Okay, now coming over here, there's another way to write POH, and it's this. pH plus POH always equal 14. So usually, if you're asked to solve for POH, you were given the pH. So you just have to take the pH and subtract it from 14. You with me on that? So let's do this. We have pH equals, we have POH equals, we have H plus concentration equals, we have OH minus. And I will give you the pH is 8.35. See if you can solve for the rest of them. So the pH was 8.35. That makes the pOH just 14 minus this, which was 5.65. Did I do that math in my head right? All right. Then, to solve for H plus, we need to take the inverse log of the negative pH. So that's 10 raised to negative 8.35, which I just wrote it, but I would calculate it. What did that answer end up to be? Which one is that one? That one? Nope. All right, someone give me this answer right here. 3.47? 4.47. All right, so that's that. Oh, times 10 to the something. Sorry. 4.47 times 10 to the negative 9. Then, to find OH minus, you can do it in two ways. You can take 1 times 10 to the negative 14 and divide it by H plus. And that will give you this answer. Or, I don't do it that way. If I know the pOH, then I just type in again 10 raised to the negative pOH. It will give you the same answer either way. And I don't know. Anyone have that one? Is that this one? All right, 2.24 times 10 to the negative 6. Either way that you calculate that, it should give you the same answer. It might be off a tiny fraction because of rounding one way or the other, but it should work. Now, look right here for just a second, and please always make sure you do this. These exponents right here, they should always add up to negative 13, negative 14, or negative 15. If they don't, then you did it wrong. And the reason I want you to double check that is sometimes you don't do your order of operations right, and you get negative 22 or something up here. Okay? That just is because you didn't bracket things right. So double check. These should always add up pretty close to negative 14. So negative 13, 14, or 15. If they do, you're probably right. If they don't, you need to check your math somewhere. Okay, fair enough. All right. Let's do the same thing, except I'll give you something else. There's a lot to erase, isn't there? All right, let's just say I know the concentration of OH minus is 2.1 times 10 to the negative 4th. Will you try and figure out all the rest? All right, so I'd probably use this number to find that one. I would take 1 times 10 to the negative 14 and divide it by 2.1 times 10 to the negative 4. Now, if you went a different order and you went like pOH to pH to H, that's fine. It's all one giant circle, so it doesn't really matter. So when we divide this, what do we end up getting? Negative what? 11. All right. Now from here, I'm ready just to find my pH and my pOH, right? So to find either one of these, I just take the negative log of these values. And what did we get for pH? 7.32? Wow, I'm struggling today. Oh, that's just terrible. 10.32. All right, so we must have got 3.68. Okay. these definitely are on your exam and definitely are on the AP test. Like they're math-wise, they're on the easier side of everything we have to do. You okay with these? Okay. Maybe tomorrow at the start, I'll give you like a tiny little quiz. Not on your grade, just to double check you're all there. Okay. So the pH scale, this is a slide from my normal chemistry class. This is all in the book, which I'm sure you're all reading intently. So it says the acidic, basic, or neutral character of a solution can be measured and reported using the pH scale. So this is all the qualitative information on it. pH is shorthand for the concentration of the hydrogen ion. pH values commonly range from 1 to 14, although some may be outside that range. A pH of 7 is neutral. pH values greater than 7 indicate bases. The higher the pH, the more basic the solution. Now, most acid and base solutions occur in water, therefore we must consider that equilibrium. As the solution becomes more acidic, the H plus increases, the OH must decrease, and then vice versa. Okay, we've gone over this actually in chapter 4 before, and this chapter, and it's in the book. Now, there's this cute little picture that I would like you to put into your notes if you're a note taker. Now, what this is showing you, it's kind of hard to see everything, I guess. Let's see here. So right here it says acid. It says neutral, which is easy to read, but then base. This picture is really good at just visually showing you the definition of acids and bases as far as H plus and OH minus are concerned. And it's good, this rainbow, which if you want to color, you can. The colored pencils are to my left. The bell rings any second, I guess. But it shows you like what indicators do when they're in acids and bases. So the Roy G. Biv, all the Roys are over in the acid, and the Bivs are here. Blue, indigo, violet, and typically neutral in almost every indicator is your green.